Hi everyone. Today me and Tigran are going to present our capstone project, which is a time measurement system for sporting events. Our supervisors are Vagan Tukhan and David Markosyan. We are going to talk about a little summary about our project and the slides and what to expect. We're gonna, of course, talk about the motivation, how everything started, how we've set on this journey. We'll talk about our system, the different use case scenarios, how we did the market research, the hardware selection, the overall architecture of the system, the assembly, and of course, hands-on experience and some software which went into our system and the upgrades we are envisioning for this project. Let's talk about how this journey began. So both me and Tigran actually have participated in Yerevan Marathon in some way. Tigran ran 5 kilometers and I was a volunteer during this event. And after these volunteerings, I've become inspired and have, thanks to Ms. Satanik, got a chance to pay Yerevan Marathon back with helping them something. And of course, encouraging a healthier lifestyle to everyone. So the goals we have set in front of us were very clear. So we needed a functional time measurement system which could store the information using RFID tags. Why RFID tags? Because it's the most common technology used in racing events such as marathons. And having a smaller in-house build, a cheaper alternative than to the system which is used now. So we have envisioned some use cases for our system at the beginnings to not only limit ourselves to the marathons, but include bicycle races and drone races. Of course, we've achieved some of these envisioned use cases, but some are sadly left for future upgrades. What requirements did we need to have this functional system? One was the real-time data collection. So if anyone crosses the line, we need to see it. We also need to see the unique tag. So from RFID, we need to read which runner crossed the checkpoint or the finish line. And of course, we needed some sort of visual feedback so the people would know that, for example, our runner 1 has crossed and won the marathon. So we've come up with this chart which shows what the system is supposed to be and how it's supposed to work. We can see that we have two different readers. One is an ultra-high frequency reader and one is a low-frequency custom device which we actually built in-house. And both get information from RFID tags. Both transmit to a Raspberry Pi, which shows it on its display, and also uploads it in the cloud in a database in its own IP address. So market research. At first, we needed to know what type of ultra-high frequency reader should we use. So after a long time of research, we came to the conclusion that these two are the best variants, and we chose the Chinese variant because it's much cheaper and offers the similar characteristics as to the American one. We had to then set up our ultra-high frequency reader. So as you saw on the slides before this, we used a Raspberry Pi, so it acted as a central controller and connected it via USB to RS-232 cable to our ultra-high frequency reader. And of course, we've connected to the display. So this is the mock photo of the setup in early stages. So you can see everything, the RFID is here, everything's connected to the display. Then Tigran will continue to talk about the custom device.
The custom 125 kilohertz antenna that we built here was basically, you can see the flowchart. It is a resonator circuit, which basically means that it includes an inductor that transferred the PWM signal from the ATtiny13 or 25. That would be the microchip that we used. Then the programming the ATtiny, which was another challenge for us, but we got help from our supervisors. Then we created a PCB, which you can see here, but this is only the first iteration of the PCB that we have, which I will come back to it a bit later. And then, of course, putting everything together and make sure that everything works. So here you can see before to move forward and build the PCB, we wanted to make sure that the circuit that we envisioned ourselves works. And this is like a very, 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 very early stage breadboard circuit that we wanted to show, and everything has been transferred to the PCB itself. However, during the printing of the PCB, we noticed that when it came back to China, we noticed that the manufacturer had some connections wrong. So I went to check the schematic to be sure if I wasn't wrong or if the Chinese are in wrong. But it turned out that they had some misinputs. So I guess it's on them. and we were sure that the breadboard circuit was working. So it's clearly on them. So this is the second iteration, and a small animation, as you can see. It is a bit different than the first iteration, of course, and it is improved because we had a hands-on experience with during the marathon, and we got some inspiration from that, which again I will address it a bit later, but still. On the actual PCB, we used an RS-232, which is basically a serial data transfer port. However, on this one, we used another port, which is actually implemented on the actual marathons right now as well. So, well, we thought, of course, it would be much easier to use that one for the people who operate the system during the marathons they know how it works, so it would be better to have that on our PCB as well. And as well as we have some ports for programming the microchip. Here you can see a better version of the comparison of both PCBs, first iteration and second iteration. And we used an op-amp, a programmer, and here you can see the microchip, the op-amp, and this is a voltage input regulator, and this is used for the programming the microchip, and this is the where we read the information when the antenna beeps, for example. Also, one notable thing, during the early stages on the breadboard, we noticed that one of the resistors was heating up a lot, and we know that the power dissipation of the simple ceramic resistors is almost like 1/4 watts, and we did some calculations, which you can actually find on our paper. We did some calculations, and we noticed that, well, actually it's exactly 0.25 watts, so maybe that's why the resistor is heating up, and we decided to use another method, using a MOSFET instead of a resistor to directly connect it to the power. So, of course, we have two different software for each of the cases, one for the ultra-high frequency and one for the custom one that we built. So addressing the first one, which is for the ultra-high frequency, is a Python code basically that runs with the help of Raspberry Pi, which we used as a brain, and it understands the electronic unique code of the RFID tag and stores it within the system, within the Raspberry Pi memory, and then sends it to the cloud that we created specifically for this application. And also it was, we have a flowchart here as well. And so you can see that the information is coming, for example, then it reads. If data is not received, then it starts the loop again. If it's received, then it moves forward and then extracts the EPC from payload, which we had to decode it from the RFID tag itself. And then it understands if maybe the EPC might not be valid, and then it moves forward, and then here you can see checks if the EPC is new. If not, it won't store the information, because we had instances when the ultra high frequency antenna was reading, had multiple readings, which we don't need because it is used in the sporting events, and it has to be very, very precise. And within our code, we have like a millisecond precision. So we got that fixed within the code itself. Moving forward for the software of the custom PCB that we created, antenna that we created, we actually used some open source materials that we found, and basically we applied it to our needs. For the ATtiny13 microcontroller, which operates at 9.6 megahertz frequency, and it generates 125 kilohertz carrier signal, and that's it. Here you can see another flowchart for the second code, which we wrote in C actually, and again, for this case, we didn't need to check if the readings has been done twice, because for the 125 kilohertz antennas, you have to bring the tag really, really close so that it reads. So for that instance, it doesn't read twice because the delay is too high. And basically, during the sporting events, for example, marathons, the athletes are wearing bracelets, and in the checkpoints, they just bring the bracelet close to the antenna, and it ticks, and they know that everything is fine, and they can, for example, continue their marathon running. Then a bit about signal modulation that we have here. We know from physics that if the frequency is lower, then the wavelength is basically a bit longer than for the higher frequencies. However, we know that the RFID tag is RFID itself, the signal, is like a electromagnetic signal, and the how it understands that the tag has been, I don't know, crossed between the tag emits the signal back to the antenna, and it receives back the every information, and understand that for example, the signal has been like changed. Here you can see the picture from the oscilloscope that we had, and basically the lower frequency tags rely on near field magnetic induction. However, the higher frequencies rely on some other modulation. So that's why it's a bit different in this case. So the lower frequencies are for close distances, and the higher frequencies are for longer distances. And also one notable thing that you have to bring the RFID tag for the lower frequencies really close, because there might be in a shell or of plastic. I mean, you know the door when you open it, right? The damaphone they call it, right? And it's basically in a plastic shell, and it's almost the same. So that's why it penetrates the 125 kilohertz signal, penetrates that kind of materials. However, the higher frequencies do not. So that's why during the sporting events, they're wearing like this numbers which on which the tag is attached directly, so that whenever, I don't know, the antenna is put, it reads the data automatically.
And about the hands-on experience, what we learned during this part, we've learned that some of our concerns, which were, what if the antenna detects like people earlier? We've noticed that during real-time testing with the same RFID technology, it doesn't happen. So if runners most of the runners got detected from this line, for example, and it read like it read everyone's number and time from that line, so we didn't get the error which we were afraid from. The other thing was, what if a lot of people during the checkpoint, not a lot of people cross at the same time, so the bracelet technology will work, and they won't like just get in a big queue to line up and to like put their bracelet near RFID.
Also, this is like some real-time testing to show how the information is stored and how it reads the data. So this is basically the second. So this is basically the information from the
Raspberry Pi. This is on the Raspberry Pi, and it shows the positions and the time, and this is already in the IP address. We see.
Oh, sorry.
Just let the video. Oh, okay. So we see the electronic product code, so the unique IDs. We see the times, and it's like very precise. So it's it wouldn't happen that like a lot of people would cross and somebody's time got lost because it shows precise time.
So for the future work, we want to connect the PCB, which of the second iteration, obviously, to the higher frequency signal and use it with the Raspberry Pi. Of course, which brings us to the second point, which is the multi-antenna system, where we have like multiple antennas connected during the finish line or the checkpoints. And also we want to optimize the UI for users and for the race organizers, because you saw the in the video, it was like really raw, but with the use of some programming and like some SQL to extract the exact data that we need, we would achieve that easily.
Perhaps the one of the upgrades, which is the saddest, is having the new version of the PCB printed and delivered. We're currently waiting on from the manufacturer, and of course, one more advantage of having like tested with the real equipment which is used nowadays, we've learned a new function which we didn't know, that it connects to the internet and transmits data to different devices. So the checkpoint and the finish line are connected via internet. So I think to conclude, what we have support an accurate real-time tag detection and timestamping system. We have it's adaptable for various races. Of course, drone races should be in future development as well, because the ultra high for the lower frequencies, it would be hard for a drone to get close to the reader. We have also made the much cost-efficient alternative. The low frequency costs very cheap, as you noticed. This costed much more. Of course, we're ready for any future upgrades
that might come up like in the future, obviously. So again, special thanks to Miss Atani, because she was the person who had the idea of bringing this up. Avet Markosyan, one of our supervisors, who had done titanic work in helping us. Of course, Vagan Tukhayan, who had helped us with some software, and also our peer engineers who helped us along the way and ordering the PCBs and in building the circuits. Thank you.
A very quick question.
Yeah.
Maybe I missed that in the beginning, but have you done a study of what's available in the market?
Yes, exactly. I wanted to say actually. Sorry. Since Sergey mentioned earlier that we both participated in the races, and we had some hands-on experience with the antenna that they are actually using right now. So we wanted to build something really close to that, but again, cost efficient, not to waste a lot of money ordering it from somewhere else and like bringing it here. Because if I'm not mistaken, it's like the entire 8 antennas and the control panel is like somewhere $6,000 each. So I mean, this solution, I know it's like a lower frequencies. Those are again ultra high, but we have the vision of bringing it up bigger so that it works in the way it should right now.
We're hoping that this is a continuous project, and even if the low frequency solution is somehow deemed that it's not effective, or somehow the races gets doesn't get the result that they want. We have the other alternative is using the Raspberry Pi system, and it's again much cheaper with just having these readers like this and connecting it to the Raspberry Pi than ordering like the full devices that are already connected and programmed, which are available in the market.
Have you compared this to other technology like wearable GPS trackers that are used for bike races or whatever?
Yeah, the one thing that is like really close to the, for example, for this one specifically, the lower frequency one, is the, as I mentioned, the Tamaphone text, because like they're using exactly the same system but like in a bit different manner. So that would be the like we have actually not bought but borrowed that secure RFID locks to understand how the circuit is built to like mimic it in some way in our circuit, because I mean it was somewhat of an inspiration.
For
I was
GPS,
asking about the GPS trackers.
Oh, okay, sorry.
High speed races, etc.
for GPS, we know that it's much heavier technology. So RFID I think is very light. GPS assumes a bracelet, which is an electronic device connected, but the RFID chip is light and it's just only like some grams of difference. Perhaps that's why in the initial phases we went with RFID. One of the advantages was that because of the GPS for marathons, it's going to be attached to your body, which may feel like may somehow hinder the performance of an athlete.
Well, it still needs a battery to operate.
Yeah.
Yeah, and RFID.
I'm looking for.
RFID is like a
RFID does
magnetic,
not
yeah.
need a power source.
Mm-hmm.
Can you go to page 14, please?
Sure.
Is there a specific reasoning for the routing choices on the second iteration? Because I see a couple of 90-degree
Differences?
angles and no grounding on the layer.
No, so it is two layered. So we have
The ground layer under.
yeah, on the bottom. Yeah, I don't know why
What
we
about
didn't
the
put
routing choice. Well, I'm
for the
just
routing
saying,
choices.
has there been impedance matching that you've been doing, or what is the choices basically?
Well, actually, I try to be as not to be messy, because like we don't have too many materials on the board itself. We checked the impedance. I think we simulated it in the Fusion, which was a new software for us, and we had to like use it for the first time and try to like to know the software itself.
Learned as we went.
But during the calculation phases, I think we were meeting the requirements that we anticipated at first. So yeah.
So, what's the fastest clock here?
I don't know. Maybe so. We have clocks in the microchip, but
That works. How about the other stuff? It's not any clocks floating around except the.
yeah, no. The only clock is in the microchip itself, because again, it's not too complicated circuit. Oh, sorry.
This is great. I mean, you've got a whole system working, talking to each other, so it's great engineering. My question is a practical one. So we're going to actually deploy this in a marathon,
Mhm.
and while the checkpointing doesn't have to be that accurate, you know, the two Kenyans that are running and are within the finish line within 2 meters,
Yeah.
can this system tell us who passed the finish line first?
Yeah.
How accurately can you tell? I mean, if it kind of picks up something in the 1 or 2 meter range, and the two Kenyans are neck and neck, can we tell who actually won from this system? How accurate is it practically? That's my question.
I think before like fully answering the question, so to 100% give a 100% answer, we need like intensive field testing as well, because without like I think after the full development of the system, we need to field test it with like very close and actual athletes who run at a faster speed when we couldn't test it like in our lab and ourselves, because it just milliseconds But hopefully, because it shows like the fraction of a second, hopefully it will work. Tigran was to add something.
So actually, yeah, in the video, that was for the ultra high frequencies. We showed that I think the difference was like I don't know, 4 milliseconds or something, because me and my friend were like running really close, try to mimic that situation, because we received that kind of feedback in the early stages of the development. So we were
But is
hoping.
there a chance for the system to pick up one runner that's behind the other runner first?
Actually, I'm sorry. So in the paper as well, we mentioned that the positioning is also playing a crucial role in the reading the data, because again, this antenna can read data from like 8 meters, and we have to like put it in such a way that it only I don't know reads the data when the runner crosses like here, or not to like come here. And again, I mentioned that the higher frequencies are not really penetrating anything. So in that situation, that plays for us as well.
And the multi-antenna support will also help with that, because if you have 4 of these, they will pick up, perhaps if even one fails, the other 3 pick up the correct one. You could also like modify the code to just filter and put the correct one.
Thank you. Is there any last question?
One last question, because it's tying to directly what you just said.
Okay.
And we talked about this last semester, so I want to see if you guys did this. What is the beam pattern for this antenna? Have you looked at the beam pattern of this antenna?
We wanted to, I remember that conversation exactly, but we haven't gone too far into that, because we wanted to implement the electrical part on the
Low frequency.
PCB for the lower frequency. We wanted to build something for ourselves, not to like come here and say we have this antenna and that's it. So that's why we haven't gone too much into that. But during when we scale this up for the higher frequencies, of course that has to be studied really closely.
Because ultimately that is what decides if it's
Mhm.
going to be
This
easy
is the
to
second
position.
question, Alex.
No, it's fair. That was a calm. Okay.
Thank you.
Thank you.
Thank you.